Alright, so in today's video we're going to go through the linear regression algorithm and an implementation in C++. The link to the repository is in the description, and you can check it out over here in linear regression in C++. So if you want to have a good walkthrough that is textual, you can check out the description. I'm going to put a good implementation. It's in Python though. So that's over there. So just a quick walkthrough of the theory. So let's say you have a bunch of points, and you know that they fit a line, and you want to make the algorithm learn the line that will best fit at this point. This is where linear regression comes in, and it's fairly straightforward. What you want here, let's say you have all of these points, right? You want to be able to draw this line in this 2D plane. So what you really have is two parameters. You have the bias, so the intercept over here, and you have the slope. So if the slope is positive, you're going to get this. If the slope is negative, you're going to get this. And what you really want is just to find these. So there's many ways. You could just like try a bunch of them and look what looks the best, but in general, in machine learning and in AI, like you won't be always able to see the thing in two-dimensional space. So here we have 2 dimension. You can have 3, you can have a million. So you need to have some sort of methodology in order to find those weight easily. So this is linear regression, so it's easy. But after that, if we look at more complex formula that we're trying to fit, we need to have this methodology. So it's fairly simple. So this is the formula. We want to find A0 and A1, which is the bias and the slope. And to do that, you need to have a cost function. So here, the cost function will tell you how good it fits. So if you have a line that is just straight over here, the cost function will tell you that this doesn't fit well. If you have a line like this that is really tight to the points, then you know that the cost function will be telling you that it's better. So there are many out there. In this case, we're gonna see the mean squared error cost function. So it's just this. So it's whatever you predicted based on your A0 and A1 minus what it actually is, exponent 2. You sum this up and you divide by n. So you take the mean of the squared error. So there's nothing too complicated here. And what you want to have is this as minimum as possible. So if you could get 0, that would be perfect. But you want to minimize it. Sometimes you cannot get 0. For instance, if the points were all wiggly like this, and the formula is not the point follow a formula that is not linear, well, your cost function will never get to 0 because it's the formula is the wrong one, right? But you can get something that is like as good as possible. Good. So this is what we want to do. So now we have this. What do we do? We could calculate it manually. Like I said, try a bunch of these and then look at the cost function and then select the one that is the best. But there's a way of doing it using gradient descent. So gradient descent is it's kind of an optimization algorithm that is that will update the parameter in order to minimize this. So if you think, I have a video on this, but if you think about it, it's like you're on a mountain somewhere and you're trying to get down the mountain. There are many intricacies to this. There are a lot of flavor of a gradient descent, but in general what you have is in your cost function plane, you're going to calculate the gradients, which are partial derivative of whatever you are right now, and then you're going to follow the gradient to go down in each of the parameter directions. So that's pretty much it. There are some intricacies, like I said. You can be in the local minimums, you can be in a global minima, but like depending on which algorithm you choose, you might be able to jump over these, and depending on the hyperparameter you choose for this thing, you might like never converge and go up like this if the learning rate is too big, let's say. But those are all intricacy, but the algorithm is fairly simple. You calculate the the partial derivative. So this is the partial derivative for a0, right? So the bias, and this is the partial derivative of a1, which is the slope. And this is just some calculus. With linear regression, it's easy, but if you have, let's say, a deep neural network, it might get more weird, and you need some other algorithm to be able to calculate those partial derivatives easily. But for our cases, this is it. So that's it. And this, if you remember, this is the actual cost function that we have over there. So that's all there is. So yeah, that's it. So like here, you can follow the way we calculated this, but this is just like some simple calculus. And this we're just gonna hardcode in our C++. We're not gonna try to make a module to automatically calculate the partial derivative formulas, since we just have two parameters. And yeah, that's it. And then what you do is, since this take the cost function into consideration and the cost function take the actual formula into consideration, you just have to iterate with this for X amount of time until you find the best parameter and you're done. That's all there is. And then yeah, there's really nothing else to do. So if you want to see Python code, you can go over here. It's a fairly good implementation. If you want to see C++ code, we're gonna jump over it right now. Alright, so here we are. I hope this is big enough. Cool. So so the code is there. I've changed it from what you've seen before on the GitHub. I refactored it. So if you want to see how I refactored it, you can check out the 2 live stream that I did. But what we have now is a main.cpp, which is where the main function is to run our stuff, and then the math is just a helper functions, a helper file with helper functions to do the calculations. There are still some stuff to refactor because I'm not an expert in C++, but it's better than before, and it's kind of understandable. So if you follow this through, you're going to be able to do the next improvement if you need to. But this is more educational than anything else. So let's look at the main function. What I've tried to do here is use the same paradigm as scikit-learn, where you have a fit and then predict. So I didn't do the fit transform thing, but you have a step where you put the data and you create your model, and then you have a step where you train the model, and then you have a step where you predict stuff, and then you can use the model. There's, like I said, there's still stuff to do, and but the skeleton is here. I also tried to emulate pandas by having a data set, kind of like a data frame class, but like not that powerful, just to be able to load my stuff and to abstract that. But that's it, and the rest is fairly straightforward. So we're gonna go through the main, and then we're gonna look at each of the other stuff. So the main, we are loading the file, which is hard-coded. So how you use it is like this: you just see that thing, and then you just call it a.out. There's no input at all, and then the thing will go into multiple iterations in order to find the right parameters. And the thing is, the data set is living here. So this is the data set that we have, and then we load it, and then we're gonna use the x0 and x1 in our data and the y's in order to train our algorithm, where we're gonna iterate and overfit on it. So this is how I decided to train it. I didn't have time to put the train, test, cross-validation things because I wanted to focus on the algorithm. And then this is the training spot, and once you load the data, you create your linear regression model with your x, y. You have to tell the length and the number of predictors. So in this case it's 2, and the length is it's the length of the data set, so it's 1, 2, 3, 4, 5. 5 data points, and then you just train, and we train for max number of iteration, which in this case is set at the beginning. It's 0.1 for the learning rate and 1,000 iteration for the gradient descent thing. And then this is where we do the testing, where I just input this is x0, which is always 1, and then we have x1, which is 123. We should get 124 if our things work properly. That's what we got. So yeah, so it can work in the sense that you can find the bias and the slope that work. So let's take a look at dataset. There's nothing much here in dataset. It's just some class I created in order to load x and y from the test.csv. So it's just a dumb loop which will read line by line first in order to find the length of this, because you cannot see it, so you have to kind of read it through, and then it will read it again by mallocating some space for the x and y's, and then like he also allocated the number of predictors. So this is the x is a 2D array, and then he allocate the y, which is a 1D array, and then we read it again in order to get each of the data over here and put it into the right spot over there. So that's it. There's two loops, like we read it twice in order to find the length and then the number of predictor, and finally to be able to get the data out. You can go over it. There's nothing that interesting in the dataset class, but once we have the dataset, what we have is the x, y, and those information on the length and the number of predictor. So what's really interesting is the linear regression model, and it's over here. I've created a weight class in order to hold the weight, but it's not that important that is separated. So in the future I'm going to absorb it into the linear regression model, but what it is really is it's just a class to have the weight. So when you initialize them, you allocate some space for the weight values, and then you do the update. Yeah, so the update is doing this thing that we talked about, and what you really have here is x0 x1 over here, and here you have a time x0, which is always 1, and this is what we put to the into the test CSV here over here. We always put 1 because this is x0 and this is x1. So what we do that is that it makes the whole code a bit easier, because you don't have to have two different functions. So this is the sum of residual, so it's this part. So it's this whole part over here, and then we're going to do times the learning rate divided by n times 2 if you want to, but this doesn't really matter. Yeah. So if we take a look at it, and we put all of the spot, the multiplier is really the learning rate divided by the length. So it's the learning rate divided by the length over here. This is n. We calculate before n, and then we all of the sums, we're going to calculate the sums, and we're going to multiply this by that, and then the current value minus this will be the new value. So this is our A0, well actually our weights, right? So those are our weights. So it's the current value minus this big blob, and we have this function to calculate the sum of residual, which is it's just this is just spread I minus yi, and you sum over all of the data points you have. So the sum of residual is over here, and this is what we do. We just iterate over the whole thing, and we sum everything, and we do the current residual, which is y pred, the current prediction at I minus the actual y at I, and then we multiply this by xi times the current predictor. So if we are at 0, the predictor is the x0 with a bias, so it's 1. So this whole thing becomes nothing but the residual. But if we're on the other thing, it's going to be times this, and this is just so that we have we do as if we calculated the partial derivative. So that's it. Here you can see, imagine that there's a times 1 over there. That's it. That's how we're doing over here. It's really that sum, and by multiplying by the multiplier, we're doing by multiplying by the multiplier and removing this from the current value. This is where we get to the new value. So this is one update that we're doing. Good, perfect. So that's the weight. There's nothing else afterward. Because we did the all calculation up front to get that. This is how you update the parameters, and after that there's not much you need to do. I have a function to print the weight if I need to. This is what you see over here, just to pre-print them. But let's walk through the actual linear regression model when we do this. So the constructor, I just put the stuff at the right place, so that my x, my y's, and my length, and then I create those weights with the number of predictors, so I call the other constructor, and then this is where we get into the training loop, which is over here, and we're just going to repeat the same thing over and over again. So I create my prediction array, and then until I get my max iteration, I just keep on going. I could do some type of early stopping when I see that it doesn't move from one iteration to another. I didn't, but we could do that, yeah, for sure. So what I do first is I predict, right? Giving my current weight, which at the beginning are all zeros, what do I have as a y prediction? Once I have this, I use them to do my update, which is my gradient descent step. So I do one step in the gradient descent, and then I calculate the mean square error, and then I go over there, and once in a while I print the weights. That's it. And then when I'm done, I free my stuff. There's honestly nothing else. It's the update that does everything, and once you do the calculation, you're good, and you just put it there. So this whole thing is doing linear regression optimization using mean square error and gradient descent, and it all boils down to those two functions over here. So there's nothing that much, and in the prediction what you're doing is you just put your formula like with your number of predictor. So since one of the x is 1, it's as if we have 1 times the first bias weight plus the x1 times the slope weight, and then we can have many predictor that just pile up if we need to, but yeah, that's it. This is how you calculate the prediction, and it all boils down to this simple formula over here when you imagine that there's a times 1 over here. That's it. So yeah, and then the thing is still working. There's the math class that we're using over here, and like this is just what I put a bunch of things. The only thing that matters really is the mean squared error thing, because this is how we calculated the loss. We didn't use it for the partial derivative things because we just hard coded it, but that's all it is. So the mean square error, if we take a look at it, this thing is telling us like how good we're doing. What I'm doing here is I have the sum of the squared residual divided by n. So if we take a look at it, so we have the residual sum of square over here that we're always calling, and then we divide by length. So this is just like a wrapper function over it, so I can have the mean square error name in my code, so that it's easier to understand. And the residual sum of square is this. We always seen something like this in the previous code. We just don't have the times whatever, and here this is how I'm doing my my exponential 2 thing. Yeah, there's just a lot of for loops stuff. This is not that optimized. There's other ways of doing those type of calculations. but I think it's easier to reason about when you're just looking at the for loops. But there's definitely some linear algebra optimization we can do in those sort of things. That's pretty much it. The other thing that we see over here is for the R2 square that I'm not using, but I can calculate to check the goodness of fit of the regression. But that's it. So that was linear regression. Yeah, I hope that you enjoy it. You can check out the GitHub if you want to go through it easily. Don't forget there's also the cool article that I've put in Python. And if you have any question, don't hesitate to leave it in the comment section. So have a great week.